Okay, you have to jump into the picture a bit, Francis. So, welcome all of you, and welcome, Francis.
Welcome and good morning, everyone, to this first lecture, I think, second lecture.
Yeah, we had a course introduction on Monday, and today we're going to do some basic lab work. And instead of like a standard PowerPoint presentation style, we're going to walk out into deep water today and actually do some lab stuff live with you guys today. That's the plan. So, please be active on Slack. And you might wonder why we're speaking English. It's Francis have yet not learned Swedish proper.
Yes,
so,
still trying to learn.
So you might ask question in Swedish. It's fine, and just be aware of it. It might be easier if you ask them in English right away, because then Francis might be able to read them and understand directly, or
answer.
Yeah, and Francis will be joining us for this course as well, as I mentioned yesterday. So yeah. So let's quickly go to what we're going to do. Let's see if I can get the right view here. So we're going to have a mix of both analog and digital stuff here today. And the analog stuff, that will be our plan for today. So I'll put it here. So the plan for today is to go through the basic setup and just talk about common problems that might occur. And also, if you have like questions of any kind, just make yourself heard in the Slack group, and we'll try to monitor that during all the time. Quick talk about Atom V's code. And as you already know, Atom is the recommended one actually, just the reason that it doesn't really work with V's code, not at my computer, and I don't think. Did you try it?
I haven't tried either.
No.
But Atom is more recommended also from the Pvm vendor and also other developers as well.
Yeah. So, we'll try to stick with that. But if any of you are like crazy in V's code, please try. Please make it work. It doesn't matter. And then we're going to talk about the different types of pins we have on our board. So if you haven't seen it yet, we're going to just show the pin out schedule diagram. So you know where to find that information and what's inside of this. It's actually an ESP32 from Espressif that's inside this one. So you can find these devices in different forms. So what Pvm has done is they have it's a Python firmware on an ESP32 device with added radius. That's more or less what they've done. So
yeah, and also different pins have different purpose. So we should not, or we don't need to use blindly any pins. So we should be aware of which pins are for which purposes.
Yeah. So that's important. And then we're going to talk about pulse width modulation and also the antennas. I see now that I didn't bring any antennas. Did you bring any? Oh, great. So, and what do we actually need in antenna-wise, and why do we have to think about that? And then we're going to move on into our lab session, and we're going to do a pulse width modulation. I actually brought an oscilloscope here, so we can see what happens in real time, and this is super exciting. I can say that right away. And of course, a little buzzer, so the sound. So we will get the Pvm represented in both the graphical way and the sound way. And then ADC, analog digital converter, which we have on board. Not connected to all, and we have to talk about bits and the resolution of that port. Mm-hmm. And then it's very, very hard word for me to pronounce.
Attenuation.
Yeah, okay. Level. But we have to be aware on how that is done in code, and why does it matter. Also, when we go into this part with the analog circuits, then it's really important that you know your electric skills. So Ohm's law, I'm going to just mention a little bit on how to calculate the voltage divider and so on, but I really want you to do much of that work yourself, and also you're reading a course in parallel now, most of you, which goes through that. So, and then we're going to connect the DHT11. So this is more or less what we're going to work with, an analog temperature sensor. This is just a pull-up resistor. This is DHT11, and this is like a buzzer speaker. That's the plan for today. Should we?
You can proceed, but let me grab the antenna quickly because I also missed out.
Yeah, okay. I'll start. And that's a good thing that we're with two in here. So we can start right away. So, in that case, let's start with the analog and digital and pin out diagram. And I'm going to show you my screen. Here we have my screen. And let's see. You can find this information online. And if you just Google if you go into the PyCom documentation, you'll find this online. And why I want to show you this is that you need to know about the hardware. We're not diving deep into the hardware in this course, but you need to know where to find the documentation. There will be several courses after this one which will dive deeper into this. But when we're talking about this, you need to know that not all pins are equal on this. So some pins might only be used for GPIOs as a general purpose input-output, like a digital pin. Some pins might be used for analog readings, and that is when an analog reading here is actually just reading a voltage. And there's a lot of pins here which we might not use in this course at all. But you have a PVM pin, DAC, digital analog converter pin, touch pin, if you want to connect some kind of touch interface. There is actually hardware support for that in the ESP32. So there's a lot of possibilities. But please have a look at this one, because sometimes you end up in an example and you want to connect a sensor of some kind and you don't get it to work. And all might be because that you're trying to connect an analog signal to a pin that can't take an analog signal, or that it's conflicting with something else. Maybe it's conflicting with an antenna or anything.
So
like
did
that.
we also mention about the voltage pin, like two different pins?
No, I haven't mentioned that, so please do. Yeah.
Because some of the sensors are sensitive and they don't accommodate high voltage, like 5 volt. So we need sometimes 3.3 and sometimes 5. Sometimes maybe even higher, lower, so we need to use resistors.
I'll show your screen here.
Not to blow up the sensors and to damage the devices.
And then anyway, talking about the different pins here, this is just the schematics of the expansion board.
Yes.
So and what the expansion board essentially does is that it gives us a way of exposing the pins, so we don't have to solder or connect everything directly to the low pi, to the microcontroller. It also has a built-in voltage regulator, so when you connect the USB port up in I'll show it. Well, obviously you have already done this, but when you connect the USB port here, then you have 5 volt from USB, sort of 5 volt. It depends on
Yes,
how much you get from your computer.
Yeah.
But it should be 5 volt, more or less. And the ESP32 device, which we have in front of us, that's powered by 3.3 volts. So if you just go up a little bit, just show that, well, you have a 5 volt pin. And you should be able, if you have an input of 5 volt into your USB connector, you can actually get 5 volt from that pin. You'll get the not unregulated voltage from that one.
Yes.
Just be aware that you shouldn't use that input signal, like 5 volt, and connect it to an input on your device. Then you might damage it. So when you're working with sensors and you want to put some signal into a digital input/output or some kind, always work with 3.3 volts.
Mm-hmm. Yes.
And we can also mention that, I mean, there is a there are a lot of sensors that actually need 5 volt.
More powerful ones. Yes.
Yeah. So, and the Arduino community, I probably have already experienced that, but directly when you start Googling things, how do I connect DHT11 sensor? How do I read an analog value? How do I, well, whatever do with electronics, and you'll end up at an Arduino web page. Yeah. So, and that's, well, Arduino is really the base standard for doing these kind of things. So there is so much information out there. Actually, I think in some ways there is an advantage of using Picom devices just by that fact that, well, you have to think about how to do it yourself. You won't find as much ready-to-use material.
Yeah, they are still new in the market, but the good thing about Picom is that they are using MicroPython, which is way simpler version than the standard Python, and these Picom devices are MicroPython enabled already, so it's very easy to develop and program.
Yeah, so, and that's the main purpose. So, but just to know that when you see a lot of schematics online, that okay, this is how you connect this sensor, and then well, just be aware of that. It's often an Arduino uses 5 volt, so you'll often find examples with 5 volt, and some sensors that are labeled 5 volt. Actually, this one, the DHT11 sensor, which I'm holding in my hand here, that's actually labeled as a 5 volt sensor, but it still works on 3.3. So, but if you have a sensor that only works on 5 volt, well, obviously you should work with 5 volt, but then you might want to think about doing a voltage divider, so you can actually power your sensor and still get the readable output from that sensor. That's when you need your knowledge in Ohm's law, which you'll learn by heart very soon. Okay, should we
just to add one note?
Yeah.
There is a forum for Picom devices. That's also Picom forum. So if you want as many help as you want, there is. I think you need to open an account.
I think so. I think
and you can get basically from software helps, hardware helps, and so on. So it's very useful if you subscribe or open an account to this forum.
And it seems to be pretty lively. So but obviously that's a good way to find a lot of reference information. So which is directly related to these boards. But if you, I mean, there are other boards as well. We might mention that we have something called CircuitPython as well.
Yes.
I can show you that right away. And just to give you an idea of what this is that Adafruit, which is a large manufacturer also of embedded devices and IoT devices in USA, they have a fork of MicroPython which is called CircuitPython, which is more or less the same, but there are some differences in the language. I think it's actually not a good thing that we have two forks, but we have MicroPython and we have CircuitPython. You can find a lot of reference material for sensors on CircuitPython examples. So I'm just saying that most of them will work, but not right off the shelf, because it might be that there is some library that is called something else. But like, it's still Python, so...
A little modification might work, yeah.
Yeah, so I'm just mentioning it, so you will, well, oh, what's CircuitPython, what's MicroPython? Well, they're actually more or less the same thing, but, well, not 100%. Oh, it's confusing, I know. But let's continue to, I mean, I'm talking too much, so antennas. We should talk about antennas.
Okay, so...
And why do we need antennas? And why are we talking about antennas? Francis?
Yeah, right now for the projects, I think for lab 1 to 4, you don't need any connection. So you are working with your own devices.
Yeah.
But IoT comes with always connectivity. And the smart devices like these Pvm devices, they need to talk to each other. And when you are having this connectivity or network connection, at the small scale, they are not very expensive, but at the large scale, you need really cheap connectivity. But at the same time, since these devices are not sending large data, you are okay with like sending few bytes of data, but over a network that connect wide area.
Yeah.
So in that sense, we have multiple options that are also embedded and programmed in these Pvm boards. And maybe you can give some of the examples.
Yeah, I mean, we in this board which you all have, it's called Low Pi 4. They have different versions of the same board, but this has Wi-Fi, it has Bluetooth, LoRa, and Sigfox built in. These are all the radios that are built into this one. And when you're going to use Wi-Fi, you really don't have to care about an antenna. There is a built-in antenna on the device that is most likely good enough for your purposes. So you will be able to connect this to a Wi-Fi right away, even without an external antenna. Obviously, you can buy an antenna as well. This antenna, which we have, I think there is one antenna per device. It should be. And I know that not all of you have gotten one, and you probably won't need it until you start with your project later on. But the long antenna here, the Wi-Fi antenna, is a bit shorter, and we actually haven't bought any of these, so you will only find the long one. This is a LoRa antenna, LoRa/Sigfox antenna. So, and it needs to be connected. Actually, I don't remember. We have to look at the specifications, but at one of these connection points here. And then you can connect your device to a LoRa gateway. I'm just telling you now, so you know what possibilities there are. We're going to have a lecture about LoRa communication just later on, so you'll get that information later on. So, and just to show that this is actually a cellular antenna. So you have the Pi there, which has
LTE connectivity also.
This one has an LTE connectivity. So you have a lot of bands in here. So Wi-Fi, Bluetooth, LoRa, Sigfox, then LTE category M1 and narrowband 1. Yeah. So this can be, for example, connected to Telia and like Telenor and Tre. There is a slot for a SIM card underneath here. So, a lot of possibilities. Just saying.
A lot of opportunities also to leverage the network connectivity. Like in Kalmar, we already have LoRa, right?
Yeah, and Iveco as well. So
you can use basically free internet or free connectivity for your Pvm devices.
Yeah. should we continue? And then we have talked about common problems. We didn't talk about that.
Yes, that's also important. I don't know if you have any questions on Slack yet, but there are mainly hardware problems that students face.
Yeah.
And what are those common problems that they face?
In my experience, the most common problems have been so far, and I'm not talking about this course because it seems to have been running very smooth. I didn't hear anything during the lab session yesterday, but common problems are often like USB cables. Now we have handed out USB cables, so that seems to be sorted out. But you use a low quality USB cable, that might be a problem. Other problems are software related, so that you connect your device and it's not found, and you won't find the USB port, all that kind of things. But it seems to be working. So
yes, I mean, also one of the problems, I mean, maybe it was not discussed earlier also. Maybe you should also update the firmware of your devices, like of your Pvm device. And I don't know also how many of you have updated your firmware. This should be one of the first step before you actually start your development.
Yeah.
Because firmwares get updated every few months, if not every 6 months and so on. So there is a well-defined process of updating the firmware. Maybe, yeah, you are showing already, right?
Yeah. We can do an update right away here, and you can see here now I have my Atom running in the background. I'll actually just disconnect these devices, the device here, so it won't interfere with the Pvm upgrade.
Because you cannot use the same port for the two purposes.
Exactly. So it might not work now when I might even need to close the Atom. Let's see. It seems to work.
It should work.
And I think I showed this the other day, and as it is no one that has said anything, it might be fine. But there are a couple of different firmwares you can choose from. There is one called PyBytes, which is the standard one, and that's their own firmware. And it contains, what's the difference between these firmwares, you might ask? Well, it's still MicroPython, all of them. The PyBytes firmware, that contains some built-in libraries which are used for their own PyBytes platform.
So it's very easy to connect to their cloud platform. Yeah.
So, in theory, it should be the legacy firmware, which we should use. Like that's the core MicroPython. So it doesn't contain any PyBytes. Well, if you're not going to use PyBytes, which is their own like online platform, well, I usually recommend that you flash the legacy firmware. Mm-hmm. But I'm saying this, we experienced this during the summer, is that they don't send updates as often to this one. So the most stable firmware is actually to use the PyBytes firmware. But there's a lot of things happening fast in this area, so you need to know how to flash the firmware. Where did you find that window for the update? Is it an Atom? No, it's not an Atom. This is the Pvm upgrade tool. So it's a program you
separate
download.
Application, yes.
Yeah.
You need to download and install. And every time you want to update your firmware, you have to run that application or tool.
So I'll probably end up directly here. So if I go to Pvm and downloads, I think I can find firmware updates, and you can see here that I have the firmware updater for Windows, Mac OS, and Linux. So that's a very easy way of they have you can update the firmware using other tools. But this is the easiest and the recommended
you can also
way.
do it from Atom, but it's more complicated, and I think using this interface is even much easier.
Yeah. So let's continue. I mean, we still haven't done the fun stuff. We're just talking. That's not fun. Should we? I'll throw this away. Maybe.
And one last thing, maybe before we move to the lab session, never connect this USB connection before you connect the low-pi to the expansion board, because it might burn the expansion board. One thing. The second thing is, when this is on, so now the expansion board and the low-pi is on, never connect or disconnect any sensors or resistors or cables to the expansion board for the safety and not to the damage of the devices.
It's good that you mentioned that, because I always forget those things. But we'll try to make it very, very instructional here today. And so, great. And please correct me if I do anything wrong. We're two here, so we can, help each other out.
It'll be fun,
Yeah. Okay, should we start with pulse width modulation? I am going to show you, let's see, I'll press this one and this one. And as you can see here now, if you see behind the picture behind me, this is taken from Wikipedia. It's a moving GIF picture, which you can import in PowerPoint nowadays. And you have already, those of you that have done lab 3, you have already played around with the pulse width modulation. And just to mention, what are you actually doing? Is that you are creating like artificial sine wave. It's not very sine wave-like in this case. It's actually just on and off. But if it's fast enough, you can create a signal that it represents. Like you can modulate the power because that's what essentially is what you're doing. And this is how the duty cycle looks like. So if you have a 100% duty cycle, well, you'll just get a straight line with the signal. So instead of showing you this, I'm going to see if I can put everything together here. And I'll move down, let's check this one, and then I'll move this one down. And then I'll go to the Pvm example, and I have one prepared here, and this is just standard from you're hidden behind my Atom editor.
It's fine, yes.
I'll remove these ones and I'll try to put it here. So there's a lot of I've tried to prepare this as well as possible with with the setup. So actually we're using a couple of different video sources with green screens and everything. I think this looks pretty neat, and like the document camera above and everything. So, okay, I have my low-pi here. I'll first show you what I have in front of me. And this is a Fluke industrial scopometer, but this is an oscilloscope. So what essentially I can do with this one is that I can show the voltage, and obviously there is a time scale as well. And this one is pretty neat because it has this outer range function. So if I connect something to it, it does its best to present that information in a neat way for me. So, well, I have my probes here, and I can start measuring right away. And I'm just going to use one channel here, and you can already see that something is happening here, and that's just like flickering, so it's 0.2 voltage, but that's just like disturbance from whatever. So let's start connecting, and let's just start to see if I just take one small wire here and connect that to ground. I'll press this one here. I'll take the blue one to ground.
Maybe do a little bit zoom.
Can we zoom? Let's see. this is maximum zoom now.
Okay.
This is just a little claw here, so I'm connecting this one to ground. Let's put it here. And take away this stuff. And then we'll take another one. And there's a lot of wires. Well, not all ports are equal, as I said before, but one port that I know works, I've already checked it up, is number 12 for this example. So I'm not running any code just yet. So, but something happened. If you look here, when I connected this one, so I'll remove it, and you can see that it says that it's about 0.066. Yeah, it's noise, but it's still something. When I connect this one, oh, it goes down to 0.002. So, oh, it seems to be much more stable now.
Zero, yeah.
Yeah. So this port is, well, it's very close to ground. So, and what we can draw conclusions of that is that, well, there is actually no voltage difference between the ground and port 12 here now on my low pi. Let's see if I can run some code. And this is now connected to the low pi. No, it's not yet. Now it's connected. And I have here, I'm importing the Pvm library. So this is like the basic example from taken from the PyCom homepage. You'll find it right away if you go into the Pvm. And then I create an object here from this class, Pvm class, which I'm importing here. I'll make this channel 1. You can read up on the documentation. We can show you right away when I'm anyway talking about it. Let's see, and then we have firmware AP references, PyCom modules. No, it's MicroPython modules maybe.
Yeah.
Where do I find?
No, not
Pvm. Machine. Yeah, obviously I imported from machine. Here we have it. And you can see here that I have, this is the Pvm example which I'm showing now. It's not really the same numbers, but well, you get the point. So you have a constructor here, which you have a timer and a frequency. And there is a channel, and you can have different channels. ID is an integer from 0 to 7, so you can have 8 different
time. A couple of questions on Slack. So somebody asked, it's not allowing him to update the firmware, and it looks like the message says resource busy. So perhaps you are connecting also to Atom at the same time. So what you need to do is disconnect from Atom, your device, and then run the firmware update again. And there was also another question from Emma. What is the correct way to disconnect the USB cable from the computer or from the PyCom device? Do you need to cancel or reset the program?
No.
You don't need to do anything. Simply disconnect one end. It's always safe to disconnect that is on your computer side, or that is not on your expansion board, because that is more sensitive board.
Yeah. So, and good that you mentioned that. I mean, I think I did that. But if you're going to connect and disconnect this one, I mean, it's just convenient sometimes to use this cable. But if you do that too much, this port here, it's more sensitive than your USB port in the computer. It happened to me once that I accidentally cracked the USB port here, and then you need some good soldering skills to get that working again. So, well, it's not destroyed forever, but well, you need to solder a little bit and be very careful. So short story. Please use the USB port on your computer when you're disconnecting the device. But you don't have to care about whatever that is running on your device. When it's powered off, it will obviously just power off, and you won't destroy anything. So that's...
Sorry for the interruption.
No. That's the point of us two sitting here. So, and I know that everyone is very excited now of what will happen on my oscilloscope here. It still says 0, and I'm going to move this window away very soon. But I can have 8 different channels according to the documentation. So I could actually have different Pvm channels operating at the same time. Mm-hmm. But you can see here, I'm creating a Pvm object, actually not the frequency of, it's actually 100 Hertz as I have it here. This could be any integer between 0 to 7 according to documentation. And then I'm using pin 12 and I'm setting that to the duty cycle of 50%. And what does that mean in... Let's see if I can find a paper. So let's see. I'll start with duty cycle. I'll do like this, and then I'll press play. Something happened, and you can see now that there is... well, I don't think you can see it very well, but I can say that it's
close to 3.3.
Yeah, 3.3 volt, and it's a straight line here. So I can manually change the duty cycle in the REPL interface down here. I'll set the duty cycle to 0 instead. And if you look at this one now, it automatically moved down. It's still a straight line. So you might worry why all this buzz about the frequency. But if we're looking about the Pvm here, so this is time and this is the voltage. And let's see, I'm trying to say, like, create a duty cycle of 50%. So from this one to this one, and let's say, sorry.
Yeah.
Don't forget about that one.
one cycle.
Yeah. This one, this distance, that's the frequency which I have. And the duty cycle is how much of this area that is like
active.
So if I have a 100% duty cycle, obviously I'll get a straight line. I won't even see whatever happens down below. So that's really no point of having a pulse width modulation with 100% duty cycle. If I have 0, obviously you get nothing.
No voltage. Yeah.
No. So let's get to where we want to be. Let's write 50%, 0.5, and let's see what happens now. And you can see that I'm writing 0.5 here. Oh, yes. You can see here now. Yeah, I know it's not super clear, but I have something moving around here. And it's... try to make this a little bit bigger. And to show you what I see here is that you can see that you have a diagram that goes up and down and up and down. This up here is, well, 3.3 volt. This is 0, and the x-axis here is time. So from this point to this point, as every square here is 2 milliseconds, it should be 100.
So this is the
frequency.
%? Yes.
Yeah. And if I write like
so
10%, you can see that it's a very narrow line. If I write 80%, well, it's almost filled, and
So 80% of 3.3 is 1.30.
yeah, that's the root mean squared value of the voltage, which is calculated by the oscilloscope. We won't dive further into that, but this is a very neat way of like dimming a LED diode up and down. You can use this one, and well, obviously we can represent this in sound as well.
Mm-hmm.
So
Yes.
let's try to do that. I'll remove this one, and then I'll just disconnect everything. I'll start with a duty cycle of 0, so I won't spoil the surprise for you. And then I have a small little buzzer, like a small little speaker. It's only 2 connectors. And if I put power on this, well, there is a small magnetic field that moves inside. And try to see if I can. Now I am doing all the fun stuff. Let's see. Duty cycle 50%. Oh yes. And I'm not sure if you can hear this, but this is 100% and a 50% at 100 hertz. And if I have 70%, well, it sounds a little bit different, but actually the hertz, well, it's
changing.
And let's see what happens here. 50% here, and then instead try to change the. I'll just copy this one down. So I'll create a new object here.
The new frequency.
2000 hertz. 3000. Okay, this is it's getting annoying. 4000, nothing. Okay, so I was starting to think this might be that I'm too old to hear this, but I think it's the speaker that might not handle these high frequencies. But well, let's just disconnect this one. It's too annoying. But now you have a representation of well, you're always behind something else. Very sorry about that. I'm going
fine,
to so like this.
To be behind the scene.
Too much things on the screen at the same time. Okay, but now we have talked about PVM. I've shown the oscilloscope. Talked about the duty cycle. What are we actually doing? Represented in both well on a screen and sound-wise. Should we go to the next point? ADC.
Yes, but we want to have a short break if you want.
Yeah, maybe that's more for us than for them. Maybe a short break. Okay, let's have a short break then. I'll press the 5-minute button. Is that okay?
Yeah.
Yeah, okay. to mention. Okay. Okay, we're back. Hope you had a nice break.
So
there was some questions about PyByte's platform on the Slack channel. I might mention that when you do your update on using the PyCom firmware, don't really worry about clicking into the PyBytes. You can just unclick these things, and even if you connected to the PyBytes platform, that's fine. Everything will work, but it's really not necessary to have like a Wi-Fi connection and your device connected to an online cloud service when you're blinking a LED. It's really no point. So skip that part until now. And if you really don't want to dig into that right away, well, fine by me. But then you'll find all the documentation online. There is substantial amount of documentation for the PyBytes platform. You'll find it online at PyCom, the documentation under PyBytes. So I think you'll manage. I think you have to create an account too.
yeah, it's a little bit also complicated. Like you have to add your device and activate your device and so on.
Yeah.
So,
but keep that
for now. It's better to skip that part.
Yeah, we'll start with the basics, and then the progression is upwards after that, and you'll be there in no time. I'm sure of it. And one thing that I just want to mention is the run versus upload project. And you can see now I have my Atom window here in front of me, and you can see that I have a couple of buttons here. I have one called Run Selected File. When I press that one, I will run whatever file I have open. So the file that I have open here now, it's just a couple of lines of code, and I will run that on the device, so on my PyCom device. But I mean, if you want your code to stay on the device, and well, you have written a good program that blinks a light, and you want that light to blink even though it's not connected to your computer. Obviously, you want to put your code on the device, and then it's when you press upload to device, upload project to device. And what does that mean? Oh, it means that you will upload a project. And what is a project? Oh, the project is what you see here. So if I press upload project to device, I'll get all these folders uploaded. So it's really not an ideal situation at this moment, because I have a lot of examples here. But for instance, let's see, I have my other Atom here. And you can see here, I have a project. And a project can contain, like, the base folder is what is called a project. I can have many projects open here, but I'm only one active at one time. And when I press the upload project to device, that active project is uploaded in full to the device. And then it will automatically execute that project when the device is powered on. So it's automatically activated. And I mean, if you might already be aware of that, how do I empty the PyCom? We just remove the files. So you could either flash it just by erasing everything. There is an option when you flash the device, but that's not really necessary. Just upload a new project, and it will take away the old project. It's that easy. So Johan, as you said, you really don't need to think about emptying the PyCom. When you just upload a new project, whatever is on will be removed.
Yeah, if you have, let's say, multiple projects, and definitely each project has a main file. So the latest main file will be replaced with the existing main file in PyCom device. So whenever you update a new main file, that main file will be always executed.
Yeah, and well, just to mention is that whatever you put in boot.py will be executed first.
At the boot time, yeah.
Yeah, and then main.py. So that's how these devices work. So you always put your main program in the main.py. And obviously, if you have libraries of any kind, put them in the /lib folder. You might put them in everything in the root folder, but we're going to talk about code structure and code quality and all that stuff a little bit later on, but it's a good way when your program grows to keep a good structure on where you put your things. So this might be like just the basic code, and then you import a lot of functions from your structure underneath. But that will be in this project structure which you have in front of you. Okay, so but let's continue to the next analog and digital converter series. I have an example here somewhere, and let's start with this one here. Sorry, everything is awkward for me. This is a small thermistor in Swedish. And you can see it's right up here. It's that small little thing here. And what is this actually? Yeah, it's actually a resistor that changes its resistance according to the temperature. So this is a temperature sensor, which we're going to try to read.
So it's an analog sensor.
It's an analog sensor. And what do we mean when we talk about analog and digital in this sense?
So basically for the digital sensors like this, or there are most of the time you have digital sensors, so you are getting the values directly out of the sensors, the measured values. So you don't need to do any types of conversion, any types of program to get the actual values. But when you are reading those analog sensors, they are getting you the value. For example, this is a temperature sensor in the form of voltage or in the form of current. So using that voltage value, you have to convert it to a readable value like digits or numbers or and so on. And this will be a simple example that we are going to show how you can.
And when we won't dive into the basics of the analog digital converter, I mean that's one part of itself. But let's just say that this is a microcontroller. It's a computer, and you already know that. You talk about bits and bytes, and that's basically just digital. Everything is digital on here. And we have an analog value. And what we mean with an analog value is that you have something that is, just on a sliding scale between 2 points. It's the value that you get out from this one. It's not 0 and it's not 0 or 1. It's something in between. It's in a range. And you want to convert that range. In this case, it's voltage. So we want to convert that voltage. That's
so it's 0, 1 in a sense. It's a 0 and 1 voltage, like in the that we saw in the machine.
Yeah, and we want to convert that to something that we can read, a number on our device. And that's when you use an analog digital converter. And these are built into the device. So we don't have to care about the electronic stuff, but we need to know how to use them. And
how to read them, yeah.
Yeah, absolutely. So let's just go into the documentation, and we can look here that we have the analog digital conversion here. And it's very simple that you have import machine. So a lot of libraries are found in the machine library. You don't have to care about these libraries. These are built into the firmware. So when you actually flash the firmware, they are automatically already included. And that's where the difference is between like CircuitPython, MicroPython, and so on. Sometimes you want to, you will very soon stumble on that, okay, you need an extra library. well, you have to download it or write one yourself and then put it on your device. But this, we're talking about built-in library functions. And you won't find the machine library on Python. So this is for MicroPython, and this is for this hardware. So we create an ADC object. Obviously, this could be named whatever, and we have to define a pin. And as I said before, we can't use any pins. We need to know.
So basically, on the expansion board, pin 13 up to pin, I think, 20 is for reading the analog signals.
Yeah. And so in this case, I'll connect this one to pin 16, just following.
So you
the
can use
basic
pin
example.
16, you can use pin 13 or
Yeah.
any pins between 13 and 20.
And then you read the analog value by just calling this function.
So if you read, so you are creating the ADC object here, and then when you are calling that object, like if you go to the up a little bit, yeah, so basically it reads the voltage in the third line. So value equals to a pin within the bracket. So it's the value is basically the voltage value, and then you need to.
Yeah, and what we need to mention also is that when you init this, this is the standard setting. So bits equals 12. So when you create this, as you see in the example here, when we create this object, there is no parameters. So the default is 12 bits resolution. And I want you to think about this because this is one of the questions in the lab number 3. So I won't tell you too much, but what does this have to do with whatever we're doing? I mean, 12 bits, 8 bits, 9 bits. Oh man, we're not talking about computer games from the 80s now, are we? No. We're talking about reading an analog value. So think about that. We'll just probably see some examples on it later on, but this is what we have to work with. 12 bits is the maximum resolution what we can get from this device. And what is also very important when we're working with the ADC, and this is very specific to the ESP32 device. So if you're working with an ADC on an Arduino, it doesn't work the same. But you have this attenuation level. Very hard to pronounce. But depending on what voltage range you are going to read, you have to specify. This is a way of specifying the range. And if we look a little bit down, is that if the 0 decibel attenuation, it actually measures only up to 1 volt. So whatever value you're reading, we talked about earlier that when we have 3.3 volt. But if
that's the input voltage.
Yeah, but if we have an input voltage which is above 1 voltage and we don't specify any attenuation level, everything above 1 will be like the maximum. So 1.5 will be the same as 2 and 1.1. So it actually will only measure the range between 0 to 1. I can raise this level. So I could actually make this up to 11 decibels, and then it will be 1 volt will be registered as 0.3 voltage. And obviously I've created a broader range. It will be third time of that. So I have the full range up to 3.3 volt, which is good. Yeah. So, but also when I'm doing this, I'm losing resolution. I'm actually, because it will be the third, a third of the resolution. You can read up more on this. So if you really pick about getting the best resolution from your ADC, you're actually losing a bit of that resolution when you're doing this, because it's basically just upscaling this. Yeah. Okay, but
and also another I would say, drawback of these analog sensors, that you might not get always precise values. So it could be somewhere that you are expecting.
Yeah, but it should be near enough. There is some calibration that can be done, etc. But yeah, but just to mention that the ADC pin input range is 0 to 1.1 voltage. The maximum value obviously up to 3.3 using the highest attenuation. And don't exceed 3.3 voltage. You might damage the device. So now we've said that part. Let's just see what we can do here. I'll have one here. I'll actually going to hide that a little bit. And
yeah, simple example.
I'll make a new one. I'll put it here. Okay, so we have now a import machine, import time. Actually, I'm not sure why I put that in there. It might have just stuck along. We'll create a pin 16 object. We have it here. Let's connect our little thermistor here. I'll connect it to the breadboard. I know it might be a little bit fussy for you to see this, but I hope you get the point. I'll make this a little bit smaller so we can both see each other well here. And as I mentioned earlier,
you can move a little bit right.
Yeah, as I mentioned earlier, this sensor, this might not affect all of you, but there is actually mislabeled from the manufacturer. So those that I bought from ElectroKit, shame on you, they are mislabeled, and I got aware of this late afternoon, night, when I'm going to just try this out. I didn't get it to work at all. But I tried and then eventually I found out that, oh, it's mislabeled. So, but what we have here is a thermistor which is already connected to a 10K resistor. So we already have the voltage divider ready to go. So we have 3 pins on this one, and you need to use all of them. I can just show you how this looks, and let's see, I have my plus here, like the BCC. I'll call this the R1. This is just one resistor here. I have the NTC. This is also a resistor, and then I'll just write minus or ground. Okay, now we can see. Yeah, and so this is basically what this is, what we have here. And well, obviously we'll connect this one to 3.3 volt, and we'll connect this one to ground. And the third leg, well, actually this one. So this is where we measure the signal. So this one goes into the PICOM device, ADC. So this is what we are actually reading. We are reading a voltage here. And now we're on to your homework. I'm going to show you how to connect this and read the value. But the value that you are reading here, you need to find out how to interpret that correctly, because you will get a voltage here. You can also take a multimeter and well, try that out as well. But this value, this whatever voltage you're measuring here, will be you must make that represented as a temperature.
Celsius or Fahrenheit.
Yeah, but that's the whole point. And just, well, to give you like a basic understanding on how this functions is that, okay, I know that I have a 10 kilo ohm resistor here. That's hopefully always 10 kilo ohms, so it won't change. And then this one varies. So here is the resistor, the NTC resistor here. This one goes up and down depending on the temperature. And not like randomly. You'll find a table. There is already documented on the ElectroKit homepage. I'll put the links out there. But this is an NTC 10K resistor. That means that it has 25 degrees equals 10,000 ohms. So at 25 degrees Celsius, it's 10K. So if we are at 25 degrees Celsius, that will be 10K. And now think about what happens. And if these two are equal, well, you'll get in between. So the voltage drop here, call this delta U1 and delta U2. So the voltage drop over resistor 1, that will be equal as the voltage drop between delta U2, because these are equal. And don't forget Ohm's law. I mean, that's a pretty important thing to remember at this point. So if these are equal, what's the voltage here? I mean, we know that we have a 3.3 here, and we know that this one is 0. We're in between, aren't we? Yeah. So if we're measuring 1.65 volts at this point, we could say that we might have about 25 degrees. And what happens if, let's see if I can find a picture of that, the ADC. And well, this is just a 10K thermistor output table. Very strange, I can't see the same. No, that's your picture, sorry.
That's my picture.
You had it as well up. Okay. You see here that you don't just skip the further left column. That's Fahrenheit, which only, well, US uses. But at 25 degrees, we have 10K. So if there is 30 degrees, we actually have about 8K. So it's the higher temperature, the resistance goes down. That means that with this simple equation, you can derive what happens, and you have a table here, so you can use that table to check whatever voltage gets out of here. And I leave this as a really good exercise for you, which you might be able to combine like 100% for the electric course you're doing at the same time, because this is just the basic things. There are also, I'm just going to mention that, I've used that when I wrote my own function. You don't have to use the table and input like table values into your function. And you get like a super long function which interpolates between different table functions. No, well, there are better ways, and there is one Steinhardt and Hart equation. That's very fun. So two guys called Steinhardt and Hart, they made up this equation. And I've used this equation myself successfully when I wrote my function for reading the temperature value. And those of you that were looked closely, I actually showed it briefly just a moment ago when I put up my atom editor. But this is the basics, and I hope that you'll get going. But let's just go and see if we can read a temperature value right away. And I'll have to see, I put a picture out yesterday. Yeah. And just to mention, this picture is from Slack. I put it out yesterday. You can find the picture as well in the instructions for this assignment, because it's labeled wrong. So if you look at this one, it actually says minus on the right part, but it's not minus. it's the signal. So I'll connect the signal to this one, and plus is to the further left, which actually says signal here, and then I'll connect the ground to the middle one, and that's what I've done now. Let's see if I can read some values, shall we? And I'll run this code. Let's see.
It's not writing anything.
1881.
So that's the voltage.
Oh, that's the ADC value.
Yeah, ADC value.
Yeah, that's the raw value from the ADC.
And then here's a formula, I think, on PyCom documentation that you can directly convert.
Yeah.
This
I think
value.
there is like a pin voltage. So in this case, I guess that I get this in, it should be about 1.6. So it's hundreds times bigger. When I wasn't aware of that, but the thing is that when we're talking about bits now, let's see if I can use it. I dropped the X key. This might be a disaster. Oh, here it is. I'm dropping things. Stream. I'm not sure if we're still online.
Yeah, we are online.
We are online, okay. I accidentally dropped, a thing that messed some other things up. I need more papers.
You just use this one.
You have one there, okay. And where are we at? Here. So what we're reading now is, if you look at the A-pin value, it says 1881. And when I use the A-pin voltage function, that actually is a function that translates the input value from the ADC. But what is important is that we have a 12 bits input. So that means that we have a resolution of 12 bits. And how much is 12 bits? Take two. We have two combinations. It could be either 0 or it could be 1. So we're talking binary. And raised to 12. And how much do we get then? One could like this. 2 raised to 12. It's very interesting. 496. 4096. So this is the amount of combinations that we can get.
Mm-hmm.
And if we say that, okay, we know that we have a range of 0 to 3.3 volts. That should be the range, because we have the attenuation of 11 decibels, the highest one in this case. That means if we get, what did we get? 1881. 1881, that was like the ADC value. So if we take 1881, we have like we use that as the percentage because it's just have to calculate that. I can't do that in my head. 1881 divided 4096 and times 3.3. That's 1.51.
Yeah, in the signal.
Yeah, and don't mention that I didn't round correctly. It should be actually be 5.2 if I'm going to use the correct mathematical. But so it doesn't really. It's not that. Let's say we could also make. I'm not sure if I'm making this harder than it should be. If I take the ground one here and the signal here, let's see what the multimeter says. No, it doesn't say anything useful at all. 3.2, that can't be right. So no, sorry, it should be there. Okay, now it's right. I accidentally put, okay, you can't see, but I can. It says 1.66 here, which is actually more or less the same as the 8-pin voltage function gave us.
Exactly same, yeah.
Yeah. So it seems about right. It seems to work. But then, well, we know how the ADC input works. If you're going to write a function that well, takes care about conversion. I won't show you too much, but what I've done here is that I've used well, I can show you. It doesn't matter. I used a function here, and I used the Steinhardt equation to calculate that, and then the value is outputted as Celsius in degrees. You might want to write your own function so you actually know what you're doing. And when we're talking about the Steinhardt equation, you'll find all the documentation online. So on how to do that equation properly.
Yeah, there is also other formulas I found.
Yeah.
If you just research a little bit, you will find multiple solutions to that.
But it's important, as I see it, that you know what you are doing. I mean, that you actually know that, okay, I'm using Ohm's law, and this is a voltage divider. You need to be able to you need to be able to do these things because you'll end up in a very bad situation if you can't read up on a documentation for a sensor and well, do something about it. So we're starting to get like a bit to the end, and before we end, I'm going to show you also, I think I had it over here,
an example of DHC.
So I'll take this one up. So now we have talked about the analog sensor, which is the thermistor, and if you only have the thermistor, well, just replace accordingly in the code, because what you're essentially doing is making a calculation in a function. So this one, very interesting. This is a digital temperature and humidity sensor. Very cheap, about 30 crowns.
Yeah.
But if you buy them online from China directly, they're probably free, or well, doesn't cost very much.
This is also similar sensor, but you don't need the resistor for this one.
Yeah.
But for this one, you might need the resistor.
So this is the bare sensor, and this is soldered to a PCB. So just to make it a bit easier to lab with, but it's the same sensor. I can mention that there is one that looks like this. It's a white one. It's think it's a more expensive one, and I think it's more accurate. Well, I don't think it's more accurate. They say it's more accurate. So, but it communicates in the same way. So
Yeah.
it's very, very similar if you have this one or this one. It's not much to think about. But let's see how we can start up this sensor. And so this is how this looks like. I'm going to make it like this. This is if you're using the pre-soldered, like the PCB one. And this is how the sensor looks when you have a bare sensor. So the NC, that stands for not connected. So you don't have to use the third leg. There are a lot of schematics I mentioned before that you can find online. So this is just an example of how to connect it to. This is an Arduino Nano, but it's similar. It's very similar. So let's just do it. And I see that well, I'll connect this one here, and I have to be very careful. And the ground is the farthest to the right, isn't it? Yeah. Maybe you want to do this.
I don't remember the figure. And the third one is not connected.
You have it here.
Okay.
Yeah. So the 5 volt.
So which one is the 5 volt? Are we connected to the 5 volt?
No, we used 3.3. This is one of the examples when the sensor says 5 volt. The one-wire protocol, most sensors are 5 volt.
This is not should not be the P16. It can be anything between.
Yeah, and I've used P23 in this case. So, but it's.
Okay, let's try P.
I think it's just by convenience. I have them sorted out, and then before you connect that one, this is the bare sensor, and that might be a good thing to remember is that if you have the bare sensor, you need a pull-up resistor because the data line needs to be at it needs to have a pull-up resistor. And what is a pull-up resistor? It's a resistor of high value, so it keeps the voltage, the potential, like at one level. So it's otherwise it will be like just a floating value. So it's a way for us to make this work. So I'll connect this to 5 volt. And,
okay, we are using 3 volt here.
Yeah, but it will be fine. Okay. Connect here. And then let's see if this will work. I'll disconnect this one. And make this smaller.
So I guess they are also aware that this line is connected. And also this line is connected.
Yeah. I have actually not mentioned that, but well, if you use a breadboard, or in Swedish kopplingsbräda, you need to know how they work. Obviously, that's a trial and error thing, and you won't destroy anything, but it's a nice way of connecting things. So here I have a resistor now on 4.7 kilo ohms. I've used not 10K, but it would work with 10K as well. And in this case, I have a library. So this is a sensor library, and you can find it online. You can actually see the address, but I'd rather let you try to search for yourself and see. And I've put that library in the lib folder. And then my main.py, and you'll find a lot of examples. And in this case, I'm actually using the library here, and and let's see if it works. And just to know that I'll have to press upload project to device. If I don't do that, it won't work, because then the library won't be uploaded. I will only run like the file. And what this does is that it's using the pin function. It has pin open drain. Sleeps for 2 seconds. It gives it like a little bit of slack so it can communicate with the sensor, because now we're communicating with the sensor. It's a one-wire protocol, so it's a digital protocol. So now we don't have to translate anything. We are communicating over a bus, a digital
direct
bus.
reading, yes.
Yeah. So so now it's more, and I'm using like a library for this. So someone else, not me, have written this library. I'll show you. I'll make this, and then I'm just outputting the temperature and the relative humidity in a loop. And obviously I could send this away, and you can see that there is some grayed out code here that says pi bytes, send signal 1, 2. And I've used this code before when, if you connect this to the pi bytes platform, you can automatically, just by this like simple example, transmit the temperature and humidity to an online service and make a graph of that. So it's not that hard. But now we're talking about a digital sensor. If you instead use this one, you don't have to care about the resistor. And there is a lot of sensors out there. You can find many of them are digital ones. This is a environmental and pressure sensor. So I think the CO2 sensor.
And you can connect as many sensors you want.
Yeah. So, and this is also a CO2 sensor. They are pretty fun. We have a light sensor here, and well, you get the point. There is a lot of sensors out there. There might be. I'm just mentioning this. If someone ends up with this sensor, it looks very similar to the thermistor sensor I have here, but it is not the same. This is a Dallas sensor, and it communicates over the one-wire protocol, the same protocol that this little guy here communicates with.
Unfortunately, it has the right level, so it doesn't have the wrong level as this one.
No, but in most things you have to look carefully and see if you can find a code of some kind and try to derive. So if you have like very good eyesight, you can see that this is a Dallas sensor, and you can actually read, and this is the digital sensor. You won't be able to read an analog value for this from this one. So yes. I think we're at the end of this session, and the main idea with this session was to give you an idea on how to get going, and well, do as much as possible with the time that we have.
So there was some questions also on Slack.
Yeah.
Do the students get the sensors already, or?
There is in Kalmar, I think that those that have wanted to get the sensors have gotten it, I guess, yeah. And in Växjö, well, I think so. There should be a box of sensors. I sent one,
because
2 days
somebody
ago, yeah.
mentioned he did not receive any sensors.
No. I know that there are, there might not be like for the sensors. When we originally planned these labs, we didn't plan that everyone was going to take sensors home. But we wanted to give you that opportunity now because of COVID, obviously. So just be aware of that. There might not be enough for everyone if you want to pick stuff and get home. In that case, I recommend that you'll buy some yourself if you want to be sitting at home. There are enough low-pi devices for everyone, so that shouldn't be a problem. But sensor-wise, no, there might be a problem, I'm just saying. But there are sensors in Växjö as well, I know. I've sent them, so
Yeah, in the worst case, they are some of them are very cheap, like 10 crowns, 15 crowns, or 20 crowns.
So just walk down to Shell & Company, or they have a broad selection. I put some links in the Slack channel, and also you have some links at the GitLab repository where you can find some information. When you're going to start with your project later on, well, then you're free to use whatever. So don't depend on these sensors that we have chosen is just to get you going and reading a value.
Yeah, these are basics.
Yeah, you'll have to buy whatever sensors you need for your project later on. So there is a start kit, which is pretty good, like a 26 module sensor start kit, which is about 300-400 crowns, something like that, both from ElectroKit and from Shell & Company, and you will find the equivalent on, well, Amazon has opened up now, so you might find it on the Swedish Amazon site as well.
Even cheaper.
Yeah, so just Google Arduino sensor kit, and you'll find a lot of kits. Yes.
So I think we have covered everything we planned for today. And
yeah, almost 2 hours, and we're still here.
I don't see any interesting questions also, so we have covered most of the areas that interest the students.
Yeah. So before we leave, I probably want to say that my console looks like disconnected all the time, but it was not so yesterday. Well, Mustafa, you might want to get some help looking at that. So try to be in the lab and get some help, and also you have to help each other out. And this is one of the courses where I really want to emphasize that help each other out in Slack. You might already be using Discord for like class sessions. That might be a good way of connecting as well. We will have Amir as a supervisor and lab assistant, so I'll get out with more information on that later on. So if you have like big problems and you need help, we can get you going online as well.
So thank you for today.
Yeah, thank you.
I think I don't have anything to add.
No.
And see you tomorrow in the lab.
See you tomorrow in the lab, and I'll announce it will be a live stream on Friday as well with me and Morgan in Swedish when we will talk about the week. So see you tomorrow and on Friday. So
see you. Thank you.
yeah, thanks.